Hi, this is Nick Boris, and today we're going to talk about MIMObit and how you can use it to design antennas with it. So the objective here is to solve a problem that will have a transmitting radio, a receiving radio, and then try to figure out the capacity that arrangement would provide under certain propagation environments, and how different antenna designs on the receiving radio can affect that capacity and which one performs better. So we will start by designing these types of dipole structure antennas. To do that, we'll start MIMObit. I double click on the shortcut of MIMObit on the screen. This brings me the welcoming screen. I'm going to start a brand new project, so I click New. This tells me that I need to create a configuration file, and it starts at the default directory, which is where all the log files are being stored, but I don't want to start there. I want to start at some other place. So I'll go under Make, Desktop, create a new folder, and I'm going to call this folder Test. And in Test, I'm creating this file, which is the default config file from MIMObit. So MIMObit brings up my default config file. This config file has all kinds of input variables that are necessary for the problem. You can get a lot of detail about it in the manual. I don't need to make any changes to it right now, so I'm gonna just click OK. It asks me to save it because it's doing it for the first time. I say save. It tells me that it has already loaded. Do I want to replace it? I can say yes or no, it doesn't matter. And as soon as I do that, I get out my status window and I get out my MIMObit main window. So let's start designing some of these antennas that I mentioned earlier. We're going to go under Antennas, Dipole Array, New Dipole Array, and it brings up the window that allows us to enter these antennas. So I'm going to create two dipoles that are parallel to the z-axis. So I'm going to put down here that we have two objects. It immediately highlights that the dipole ID that I'm looking at right now is 1, the first of the two objects. So I'm going to make this resonated around at the middle of the 2400 ISM band. So at that band, the frequency is approximately 12 centimeters. I'm going to make the dipole length to be 6 centimeters, which is about half a wavelength. And I'm going to put one of them at -3 centimeters on the x-axis, and the y and the z-axis location is 0. Dipole diameter, I'm going to leave it at 2 millimeters. The object orientation, I want them to be parallel to the z-axis, so I need theta to be 0. And the type of dipole that I can have is independent, control, parasitic, and then I can also have objects that are like single screen and double screen. You can read details about these in the manual. Right now I need an independent dipole. The conductivity is that of copper. I'm going to leave this as is. And the diameter 2 millimeters. The density I can have automatic or user-defined. I'm going to leave it at automatic. Basically, here it tells me that it will use 15 piecewise sinusoidal modes per wavelength in order to do the numerical calculation using a method of modes. I could have changed it to user-defined and put down here that along the length of the dipole, I want to have, let's say, 5 modes. Okay, I'm going to save this object. Oh, the last panel over here with inputs has to do with the frequencies, and then the check mark points here indicate the frequencies at which the fields will be calculated. So if I say select frequencies, this notation up here is MATLAB compatible, and it tells us here that we're going to have all these frequency points at which we're going to calculate the fields. The S parameters of the antenna structure are going to be calculated at all the frequencies, but the checkpoints indicate which frequencies will actually have the fields calculated in addition to the S parameters. So I just checked off 2420 and 2480 so that we don't have too large files to do this. Okay, the angular resolution on the far field, I'm saying 5 centimeters, I'm sorry, 5 degrees. So dipole geometry, you can check yes or no here. I'm going to leave it as no for now. Anyway, so let me save this object. As I did, the dipole ID number 2 came up. So I need to place this at the other side of the z-axis, and I'm going to leave everything else the same. One thing that I didn't mention is the source load location here for the dipoles is indicated to be 0.5, and this means that it is at 50%, that is at the middle of the dipoles. So I save this object also. Now I'm going to save the file. I'm going to call this file 2Z dipoles at 2450 megahertz, and I'm going to save it. And now I go back to this window. It has already loaded this file with all the information about these dipoles on in the code. So now I'm going to say simulate. As the simulation is running, I get a number of warnings, or I should say status messages at the status window. These are the green messages here. It tells me that the simulation is in progress and the runtime is estimated to be about half a minute. And as you see, it has been finished. I can visualize the geometry from in here. And this shows me what I analyzed. 2 dipoles parallel to the z-axis at plus and minus 3 centimeters from the origin, and they are both center fed because I have located the source to be at 50% of the length of the dipole. I can also visualize the log file. This is the results file that came out of the simulation. So if I bring this up, it has loaded directly my 2Z dipoles, and I have all these tools over here to actually look at what the dipoles how the dipoles perform. So I can go and select the frequency, say in the middle of the band, 2440, and look at the actual active electric field that is produced by these two dipoles when both ports are driven with the same kind of source, 1-1. This is the voltage source driving the dipoles. So if I say active field, I have plotted here immediately the pattern of the antenna, the active electric field pattern of the antenna at various canonical planes. This is the theta equals 90 plane, the XY plane, and this is the 3D version of my active electric field. Okay, now I'm going back in there, back into the PlotLab utility, and I'm going to plot the total radiated power for this excitation. And this is what I get for the total radiated power with the excitation vector 1-1. Another thing that you can check here very quickly is that if I change the excitation vector to 2, and I ask it to plot on the same figure and plot the TRP again, I will see that now my TRP is, when the excitation vector is 2-2, my TRP is significantly higher because I have, of course, more power driving the dipoles. I can make any changes that you want here, and I hope that you can experiment with this as much as you like. You can calculate the envelope correlation coefficients, mean effective gain. You can calculate plane cuts at different angles that you want. You can calculate radiation efficiency. And for this particular quantity, the radiation efficiency, we have a number of options: matched, mismatched, system, and single port. And for a description of what these are, please consult the manual. Additionally, you could look at the S parameters of this antenna system. Let me get rid of some of the windows here. Before I go to the S parameters, let me actually change the structure. Let me do the following. Let me say that I have only port 1 excited, which is basically 1000, and I want to plot again at this same frequency the active electric fields. If I do that, I'm getting a significantly different pattern, of course. If you look at this particular plot side by side, this is the theta equals 90, the XY plane. And when I drive only one of the two dipoles, so my excitation vector is 1000, I get a distorted omni pattern, that of the dipole on the XY plane. In contrast, if I drive both dipoles, they do combine constructively along this axis here, which is the y-axis, and they combine destructively along the x-axis because of the separation distance between those two dipoles being half a wavelength. You can play here and get a lot of different results out. For example, if I go to excitation and I make this 1010, but I also put a phase difference of 180 degrees between them. Then I force the two dipoles to combine constructively along the x-axis and destructively along the y-axis. So if I plot the active field gain at the same frequency, my theta equals 90 pattern now looks different because I have forced the pattern here to destructively combine along the y-axis while it combines constructively along the x-axis. This concludes the design of these dipoles. Oh, let me go and look at the S parameters. You could plot any one of the S parameters, or you could plot the diagonal elements or a specific row, depending on what you are looking at. So in this particular case, let's plot S11. So if you say plot S parameters, this is what the S11 looks like. If I plot the diagonal, I should say here that this is the actual magnitude of the S parameters in dB, and this is the phase for S11. If I go here and I say plot on the same figure, and I change this to S22, it's going to plot S22 on the same figure. But because the two dipoles are physically identical, I have these two curves coincide. Additionally, I could plot a Smith chart for the diagonal elements. So that will have two plots that will follow on each other. Oops, I apologize. I needed a Smith chart. So basically I get a trace up here for the S11 and S22. Now, the results have been saved into a file. It's a lab file, and you can use this lab file to describe a radio that has these two kinds of Z-directed dipoles. We have a lot of these dipole kind of structures in the libraries of MIMObit, and I will show you in another tutorial how to bring them in and solve MIMObit kind of problems with these antennas. Thank you.